He's a professor of cybernetics at the University's Reading. It's great to hear that title still in use, going back to ancient days nearly with Professor Wiener. As well as the director of the university's KTP Center. He's held positions at Oxford and Newcastle and Warwick universities before he accepted this chair at the University of Reading. He's published 500 or more research papers and was...
Nobody's read any of them.
You want to get back to the probabilities, 500, something I'm sure they have. And was presented with the Future of Health Technology Award from MIT. His implant technology research was featured on Wired magazine. We're very pleased to have you giving our keynote speak.
Thank you. Thank you, Barak. Thank you, Temple and team, for inviting me here. Thank you, Martine, as well. A fellow co-star, I understand, from IMDb. I think the Transcendent Man Ray's film. So next we'll meet at the Oscars, I guess. So we look forward to that. We'll get the speech ready. Yes, it's nice to be here from a cautious Europe, I guess, as we've just been talking about. And I'm afraid this is going to be a little bit of a history. I know you've all been talking about the future. I'm really going to go into the past. So if you get a bit bored with it, so be it. But maybe there'll be a little bit of speculation there. It's looking at more experimentation as well, so there's not really going to be any charts and mathematics, or it's all, these are the results of what we've done. And just to get you in the mood, I'm going to go back to the last millennium, even that far ago. Radio frequency identification devices. This is to set the scene. Here's me, much, much younger, 1998. There's my local doctor. At the time, I mean, if Wikipedia is a relevant reference, it's been used once or twice, you'll see it says one of the first human trials. I think maybe it was the first, but one of the first human trials. It was implanted in my arm. That's the thing on this. This was implanted. This radio. This is just a sort of, for comparison, is a typical salary of a professor in the UK at the present time. Well, bankers, professors get a lot more, obviously, with their bonuses. And this was implanted in my left arm. What we got it to do was simply, this is 1998, so we're going way back, was to identify me to the computer in my building. So it opened the door for me to my laboratory when I walked towards the laboratory. It switched the lights on for me, said hello when I came through the front door, things like that. All fun stuff. And various people said, no one's ever going to want to do anything like this. Whereas now, I think the US Food and Drug Admin okayed the very chip for use in humans in about 2004. So there's various people with diabetes. It depends what report you read. Are there 8 or 18 or 100 members of the Mexican government that have an implant like this? And of course, many of you have got cats and dogs with an implant like this. You can rest assured that it's been fully tested on a human before your animal had the thing. It's 4 experiments. That's really all we're going to say on the RFID. Coming more up to date now, it's really raising the question about what are robots, and with the testing we do with different cultures, with growing neurons and so on, things like that. For me, as a cybernetician, it's important to put it in a feedback loop, and hence using a robot as a testbed body is very, very useful. Now, just to get us in the mood of what robots we're talking about, I've got a little clip here from a BBC programme called Inventions That Change the World. There's a robot head that we start on, and then there's some of our little mobile robots that we use. But it's just a fun clip about robots.
One of the AI community's leading lights is Professor Kevin Warwick.
Well, this is a robot head.
Dissatisfied with vacuum cleaners and robot dogs, Kevin's gone one stage further. His cyborg comes complete with
radar in its nose and an infrared top lip.
Is it intelligent?
Well, in a very limited way, I guess it is. It's sort of a basic instinct. What do I do with this information that I'm getting? How do I move? How do I operate if this signal is different?
So what's it doing now?
Well, if you clap your hands...
Oi, over here. Oh, it did it.
It's making basic decisions. All we've got it doing here is programmed to make basic decisions based on that sensory information that's coming in.
Getting the information in is nothing. That's like picking up a book. That's not an intelligent thing to do. Reading the book and knowing what the words mean, that's surely the intelligence.
Many machines can read books nowadays, but it means something different electronically to the machine as it would mean to a human.
Though the cyborg head does a reasonable job of sensing, it can't really interact with or explore its surroundings. It's fastened to its robot arm. And according to Kevin, it's only as intelligent as a dishwasher. If that's a dishwasher...
Yes.
Where are these in terms of... Are they dolphins, chimps?
I think you'd have to say it's about the 50 to 100 brain cell area. So realistically, you're talking slugs and snails.
But a slug and a snail, they know to eat. They know. These things don't...
They have some innate abilities.
There's no self-preservation with that.
Well, we do have. The power supply, they don't have their own batteries. They each have power they're picking up from the floor here. That's where they're getting their energy. That's where they're getting their food
But
from.
if you turned off this section of the floor...
If we turn off this section,
was here,
they have a basic instinct to go and look for some power somewhere else.
They
will keep going to do that until they find some.
So if I put him down...
It should go off looking...
So he'll have to go and look for power. And I got to tell him to do that?
No, it's an innate response for that robot. It's a basic thing of its life. Yeah.
No, his lights have come back on.
Lights are coming on.
So he's found power.
It's happy now that it's getting power. Away to go.
But these, then, are as intelligent as slugs.
It's different, but in terms of numbers of brain cells and that sort of thing, yeah, we have slugs. Probably you could say we're up to bees and wasps, the sort of tens of thousands of brain cells, is about as good as you can get. Yeah.
Bees and wasps.
Yeah.
Right.
There we go. I have to say again, if we use Wikipedia once more, if you check on there, the actual quote originally was that our robots have 50 to 100 brain cells, which is about the same as a slug or a snail or a Manchester United supporter. But for some reason, the BBC didn't want to put that bit in. So those robots there are they're computer-based, microprocessor-based systems. The robots we've got now, the versions of those wheeled robots that you saw, are no longer of that form. This is on the right-hand side is the robot body with the wheels, as you were looking at. But what we've done is replace the computer, the microprocessor, by a cultured neural network, a biological neural network, and on a multi-electrode array. So we're growing neurons on an array. We can send signals, the sensory signals, ultrasonic sensory signals from the robot body into the brain, the culture, and pick up signals from the culture to send to the wheels of the robot and drive the wheels of the robot around. So the robot's brain is solely a computer. It doesn't have a biological brain, as it were, with neurons that are cultured. It doesn't have a computer in the loop at all. It's just a biological brain making the decisions. This is how, just on a little dish with the electrodes, we have at the moment taken rat embryos, separated the neurons using enzymes, and then laid them out on the array, feed them every couple of days. Within about 20 minutes of being set out, the neurons are starting to make connections with other neurons, and within a week, there's enough activity there, brain activity, that we can link up with the robot and get it to start driving the robot around. and the culture has about 100,000 neurons. So it's not up to the human. So, you know, humans 100 billion or something like that. I think it's 200 billion for Americans, I understand, but typically 100 billion, which is, so it's not up to, but 100,000 is okay. You know, it's quite a reasonable figure to start with. If you've not seen one before, this is a robot, a wheeled robot with ultrasonic sensors on that is being driven purely by a biological brain. And what it's supposed to do is just move forwards and not bump into the wall. So it's supposed to, when it gets close to the wall, turn right, and then, but it's not supposed, there we go, it turns right when it's not supposed to turn right. So what this is like a baby robot. The brain has just been connected on. We've picked up innate ways that the brain operates in order to start it off. And what we're looking at is, if we put it in this corral, in this arena on a regular basis, does the habit of being put in that corral change the neural structure so that particular pathways strengthen, which it does do. Over a period of time, it goes away from this. It's like a baby falling over. It's bumping into the wall too much. After several weeks, it's moving around quite nicely just from the habit of doing that. What we're moving on to, all the 4 studies that I'm talking about, including the RFID that I mentioned, are to do with human studies. Clearly, the culture here, we can start to look at how memories are formed in the culture itself. How does it remember particular places that it's going to, or what to do in particular places? Clearly, that's much more useful when we start looking at human neurons, which is what we're doing now. So we're starting to culture human neurons to put them into the robot body. Clearly, there are a number of ethical issues. It's not such ethical issues that we're not supposed to do it. It's more ethical issues in terms of how do we tell people what we're doing. Because if the media take it, oh, you've got a robot with a human brain, then people might, hold on a minute. And as usual, MIT will claim they've already done it, but you get used to that. It's a shame the guy from Medtronic wasn't able to stick around, because I got a video or DVD that I got from Medtronic just to say this is experiment number 3. We'll see where it goes in a moment. I'm sure most of you have seen the typical Parkinsonian deep brain stimulator, but I'm going to show it to you anyway. If you haven't, then enjoy. This is an actual guy who has Parkinson's disease. He's received the Medtronic stimulator. Thanks to Medtronic for letting me show this. And you will see a before and after, and then I will explain the research we're doing in the area.
I'd like to show you in 2 minutes what was the status of Mr. Plessman when he was referred to us by his neurologist in Belgium. And you see him before surgery, without drug, unable to stand up by himself. He's helped by Patricia Limousin, who is a neurologist in our group. And he's not able to do anything of, as he will tell you, makes your life looking like normal. He's not able to walk. He has having dystonia, which are muscular contraction, deforming the different joints. And this is the best he could do without the drugs, with the help of people around him and mainly his wife and friends. He was referred because the drugs were not working anymore. He was not having any more improvement, and as he will tell you, he was just stuck to a wheelchair. This is after surgery. You see the tremor. We turn one of the 2 stimulators which were implanted with electrode into his subthalamic nucleus, which is a tiny part of the brain. And you see that in a few seconds, the stimulation induces a stop of the tremor. This is still visible on the other side. We will turn on the stimulator on the right side, and you will see something even more spectacular than that. You will see that the patient feels again free, he moves, and he resets himself in his chair in the position where he feels the most important. he will obey Dr. Pollack in doing some tests, even if he feels that those tests are a little bit useless as compared to the feeling he has. He can do that almost normally. On the right side, should I do it longer? Does he say? And he will show it on the other side. And then he will walk. He stood up alone. He's without any drug. You see him walking, turning. It was a few days before the Vienna meeting on movement disorder.
Now, there are several thousand people with that implant. The people we work with at Oxford, Tipu Aziz and his team actually fit one of these every week to a new patient. So as he's a neurosurgeon, that means probably about 25 patients a year because they have lots of holidays. But it means there are a lot of people with these implants in place. One of the problems with them is that they're constantly stimulating. So they're using a lot of power, a lot of current up, and they need power packs to be replaced. Actually, recharging them really is not possible externally because of all sorts of factors. And that means going back into hospital every 18 months, 2 years for surgery, which takes up surgeons' time. It costs a lot of money. What we're trying to do is to make the stimulator a little bit more intelligent so that it only stimulates when it needs to stimulate, not all the time. However, you don't want it triggering a stimulation when tremors have started up, so the person has tremors every so often. You need it to try and predict that tremors are going to start before they actually start. And what we're doing, the electrodes are actually bidirectional, so we can pick up signals in this case, the subthalamic nucleus, and use artificial intelligence methods, fairly straightforward ones, nothing particularly daunting, I have to say, to monitor the signals in the person's brain and to predict when tremors are going to occur before they occur. And that's what we're doing at the present time. These are some actual signals. If my brain worked a little bit better, there we go. If a machine was doing this, we wouldn't have a problem. The bottom signal, this is the EMG, muscular signal, showing the tremors. If this particular sequence, just to show you what's going on, 45 to 50 seconds, everything's all right, and then the tremors start up. So this is an indication that the tremors have started. The sequence above is the signals picked up at the same time. This is an actual patient, the same time in the patient in the subthalamic nucleus. And I think if you look at that, you can see around the 45 to 50 second mark that the variation of the signal changes a bit, we can see. Now, it turns out that in some patients, the variation of the signal diminishes, and in other patients, it actually increases. I mean, we're trying to understand what are there differences? Are there different types of Parkinson's disease? It may be the positioning of the electrodes, there's all sorts of reasons. But whatever, what we've done, just to show you what's possible, is to train a neural network, an artificial neural network, to recognize, first of all, when there are tremors, but then to predict when there are going to be tremors. We see the output, if anybody knows about this, it's a multi-layer perceptron. It's a fairly standard artificial intelligence procedure. At the 45 to 50 second mark, the output goes high. This is simply flagging that the tremors have started up. Great, fine, but it's showing it's recognized them. Around the 14, 15 to 19 second, we get some spikes. The network is saying something's going on. And in fact, if we look at the EMG signal, and maybe even the electrical signal, the local field potentials, it's as though the tremors start to get going, but they don't get going. Something happened, but it doesn't kick in. But the network has picked it up. Most important of all is this thing here, the 30-second point. There's a big spike. Something's going to happen, or something's not happening, so there must be something going to happen. And sure enough, 15 to 20 seconds later, it kicks in and off it goes. Now, we've got data now, this type of stuff, on over 200 patients and are able to train neural networks pretty reliably to carry out the same sort of prediction. This 15 to 20 seconds is perhaps at the longer end. Some of them it's about 10 seconds, but the networks are pretty clearly able to pick up something is going to happen in about 10, 20 seconds time. So what we're doing now with the surgeons is to look to apply an actual feedback loop. So to have the stimulator not working, but only working when the network says, okay, kick in, to stop the tremors, and then off we go until the tremors are predicted again. Hopefully with a view to reduce the amount of power requirements. I think one side effect of this work is not just the predictor, but the fact that something is going on deep in the patient's brain that an artificial intelligence system can pick up and predict what is going to happen in the human brain before it actually happens. 15 to 20 seconds is quite some time. I mean, you can go and have maybe a cup of coffee, I don't know. I mean, maybe it's not enough time for sex and things like that. With my first wife, it'd be far too long, but it's a long time, and you can use that to predict. It's plenty of time to apply a stimulation or to give the person an indication something's going to happen and so on. Now, as you know, the same stimulator is used in different parts of the brain for a much smaller number of people for epilepsy. And what we're doing now also is looking at the data for patients with epilepsy and seeing if we can come up with the same sort of predictions. It looks as though it will be possible. Of course, the same stimulator is used in more research cases for people with Tourette syndrome and also even clinical depression. And so there are potential, all sorts of strange applications if we can predict what's going to happen. So if you can imagine now, if we could predict that somebody is going to feel depressed, so with their stimulator it only switches on when they're going to be depressed, clearly they would be there, fine, 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 and suddenly they feel, oh, isn't life wonderful? And then they start worrying about the fact they were going to be depressed, and what am I going to, isn't that what, so you get into strange loops. Clearly there are all sorts of ethical questions for using it outside the Parkinson disease, perhaps epilepsy area. But even if you look at epilepsy, the possibility of a prediction in a reasonably accurate, I mean, it doesn't matter if it predicts occasionally that there is going to be a fit or there is going to be a tremor and it didn't get it right. It doesn't matter about that because it's still better than the system. If it gets it wrong and it doesn't predict, then that's not so good. So you don't mind false predictions, false positives, as it were, as long as they're not too frequent. The last of the experiments is the one I've been mostly involved with myself. Some of you may know about it, but let me fill you in. Reasons for it. And this crosses the boundary of therapy and enhancement. This is Campbell Aird, who lost his arm due to cancer. He's been given this articulated arm, but you see he's actually controlling it with his hand here. You'll see him flicking a switch, and many of the methods for bionic arms use other parts of the body to operate it. I mean, to me it seems a bit silly that he's having to use his left hand to control his right hand. I think the best that I've seen, Todd Kuiken's work up at Chicago, the Rehab Institute, where he's grafted on nerve fibers to muscles, but then they need electrodes on the outside of the muscles, and that limits the amount of time people can use it, but nevertheless it's excellent work. But it would be much better, surely, if we just had a straight interface from the person's brain, and we had presentations yesterday looking at that, or nervous system, onto the wires. This is where it gets fun though, because if we started, what I would look at, brain signals, neural signals if you like, not just being in the brain or nervous system, but appearing on the wires of the arm, then from a technological point of view, we can clip on those wires, we can send those signals wherever we want. They don't have to stay within the body. So if we're able to have a bidirectional interface from the brain to technology, then okay, we can look at rehabilitation, we can look at therapy, but whoa, it opens up all sorts of possible enhancement. Your brain, if you plug yourself in, if you like, can start controlling, not just controlling your body, but it can start controlling, well, wherever the internet takes you. You can start controlling a vehicle on another planet. You don't have to send astronauts to Mars or wherever you want. You can stay at home and just send a connection to your nervous system up there, and it'd be like you're there. And also you can sense things on another planet. You can sense, not just limiting to infrared, to human senses. You can go to infrared and ultrasonic. You can extend your sensory range. So if you're able to plug yourself in, then you can extend your capabilities wherever you want them to be. This is me lying on the operating theatre in the Radcliffe Infirmary in Oxford. Team of 4 neurosurgeons. What they did, some of you may recognise this. Now it's called the BrainGate system. It used to be called the UTAR array. 100 electrodes, 1.5 millimetres long. The spikes, the electrodes themselves, are 1 to 3 micrometers, that sort of size. So the electrodes are around the neuron size. And 100 of them, and this was fired into the median nerve fibres of my left arm. Here's highlights from the we haven't seen much blood so far, so here's the highlights of the operation. What you see there, this is my arm. What they had to do was to make 2 incisions, but sort of make a tunnel to start with a metal rod, and then put this tube down so that the 100 electrodes, they could feed down the tube. They then moved the tube out of the way, leaving the electrodes in position. On my nerve fibres, they removed some of the myelin sheath, put those 100 electrodes on, hammered it into place, and sewed it all up. So I had for the 3 months, just over 3 months that this was in place for the experiment, this was like an external connection from my nervous system, which we could simply plug in here, plug into the computer, or I had a little fancy radio transmitter receiver unit so we could have a bidirectional. And this was a bidirectional link, I should say, not just monitoring the signals on my nerve fibers, but we were able to stimulate my nervous system, which was important. Now, I've got a little clip from Discovery TV. Sorry it's a bit funky, but give you some idea of some of the things I was able to do.
With technology is the world's first cyborg. Part man, part machine. Kevin Warwick, cybernetics professor at Reading University, England, took a leap into the future as long ago as 2002. For 3 months, a silicon chip was implanted into the nerves in his arm.
At that time, no human had had an implant of this type before.
It was a procedure that until then had only been tested on chickens.
Would the body reject it? Would it affect the way I moved or my sensory capabilities? I could have lost the use of my hand. Could it affect my brain? Ultimately, could have sent me crazy.
Kevin was plugged into a computer which monitored the nerve signals from his brain to his arm, receiving and transmitting them as radio waves. With the signals from his brain, Kevin could not only turn on lights, he could control a wheelchair. And from 5,000 kilometers away via the internet, he succeeded in getting a robot hand to mimic his own hand movements. His most impressive experiment involved his wife, Irena, also having a chip implanted in her arm.
The communication experiment between myself and Irena was vitally important to me. This was the highlight of the whole experiment.
Kevin wanted to discover if it was possible for his brain to receive and feel signals from Irena's brain.
When Irena first moved her hand, it actually felt like a charge running up my index finger. It was a phenomenal feeling. Literally, every time she moved, my brain received a signal. There we were communicating for the first time in the world, nervous system to nervous system.
It was the first time 2 people had electronically communicated by thought alone.
In the short term, we're going to see implants used to help people who are paralysed switch on lights, operate the TV, just by thinking about it.
In 30 years, he believes we'll all have chips in our brains.
But ultimately, having extra memory, having downloads from the computer, uploading from the brain. Earth is going to be controlled by cyborgs. Humans are going to be something of a subspecies.
We'll be half man, half machine, with super memory, super senses and superpowers.
I think quite clearly that's where we're going. Superhuman. There we go, the singularity, of course. Oh, thanks very much, thank you. Yeah, I didn't want to mention singularity in the clip. Ray sells enough books anyway, so. Just a few holiday snaps to conclude with. This is wearing a baseball cap with ultrasonic sensors on it. The output from the ultrasonic sensors was fed down onto my nervous system. What was happening when an object came closer, my brain was receiving pulses of electrical current that we were feeding in, stimulating my nervous system, which my brain took us 6 weeks to train my brain to recognize the pulses. As an object came close, the frequency of the pulses increased. As an object moved further away, the frequency was reduced. So I was able, with a blindfold on, I could move around and detect objects very reliably. I didn't know what they were, of course, but I could recognize where they were. And it does give you ultrasonic input. If anybody's not had an extra sense, one or two of you may not have had, it does give you ultrasonics, quite a reliable sense of distance, which we're not really all that good on as humans. Here, Ian, my researcher, when he brought the board further away from me, brought it closer to me, I was trying to follow ultrasonically to stay the distance away from it. This is my wife, Irena, again, wearing a piece of jewellery a student at the Royal College of Art put together. I think you guys, forget flowers and things for your wife. This is what you have to do. This was linked to my nervous system. And you have all sorts of ways. It could be just open, close my hand, so neurally controlling my wife's jewellery colour. It changed from red to blue. But on the nervous system, it's pretty easy to detect different signals. I think Ros Pickard at MIT is picking up signals to do with anger, stress in drivers. Clearly, when you're calm or when you're excited, you can pick up quite clearly the frequency of the signals on the nervous system. So if you imagine here, when I was calm, my wife's jewellery was blue, and when I got excited, her jewellery started flashing red. She works in a different place to me. So if you can picture her there with her blue jewellery, starting with blue to start with, fine, he's not doing anything he shouldn't. Suddenly it starts flashing red. What is he doing? And who is he doing it with? So I don't know whether that's such a good idea. This is me. The guys at Columbia University, the real-time computing labs, helped us out. This is me in their labs there in New York. What we did was to plug my nervous system into the internet. It actually had an IP address. So if you'd have known, you would have been able to send signals directly onto my nervous system. The security was we didn't tell people what we were doing. What we did was link up to the robot hand that you saw before, the one with Campbell Aird, the same hand, back in the labs in Reading. So when I moved my hand in New York, my neural signals were sent across the internet to move the robot hand in Reading. And it mimicked, there was a slight time delay, but it mimicked the hand movements pretty well. The hand has, the robot hand that is, has fingertip sensors on it, and signals from those sensors were sent back across the internet to stimulate my brain in the same sort of way. So as it gripped harder and harder, the frequency of signals increased. And what I was trying to do without looking at it was to get the fingertips to just to touch an object, so not to, so that the signals almost died away, but not quite. And again, that worked very well. All sorts of questions, of course, in terms of the hand's mechanical design and so on, but we were looking more at the neural control of the hand. So it'd be quite possible from a neural control point of view for an amputee to have an artificial hand with a suitable interface that is reliable and durable, which again was not part of the thing, but to control a hand from a neural point of view. the final part of the experiment, which I did talk about in the discovery clip, what my wife had, you can try this tonight if you want. She had what's called microneurography. I'm sure most of you know about that. It just involves putting wires into your nervous system. So if you try tonight, just push some very thin wires into your nervous system. You will find it is extremely painful. And we thought she was going to have some anesthetic, but the doctor said, no, I need to make sure I've made a good contact here. So he pushed the electrode, and she screamed, and he said, yeah, I think we've made a good contact there. He pushed another electrode in the same way, another wire, and we went back to the lab and electrically linked our nervous systems together. So what happened when Irena, my wife, when she moved her hand like that, my brain received a pulse. And when she went ding, 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 my brain said ding, 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 3 pulses. So what we did was communicate in a very basic way, telegraphically, in fact radio telegraphically, a sort of a very simple Morse code, if you like, but it was just proving the point that you could do it. We were doing, I mean, I guess there was an electrical connection directly from brain to brain, if you count the nervous system as part of that. And if I move my hand, her nervous system receives signals in return. So it's a very, very simple form of communication, which when we're looking to brain-computer interfaces, which I know there's people talking later today and the presentations yesterday morning, I found it very, very exciting as the possibilities that are there. Disappointed to hear it's going to be animal trials first, because I'm eager to get hold of it myself. Because quite clearly the step from this is to go from nervous system to brain communication. And that's definitely what I would like to do in my lifetime. I've got a few years, so hurry up with the research. Hopefully, therefore, I would say within a decade, if the technology's there, we can be communicating directly from brain to brain in a very basic way at first. But I mean, one of the reasons for doing this is looking at how poor humans are at communication now. We take complex signals and we translate them into this stupid coded mechanical pressure wave, and then our ears, or somebody else's ears, convert the signals back. And we, of course, when you've been married for 40, 50 years, your wife still has no idea what you're talking about. Whereas if you could send signals directly between brains, it opens up all the possibilities, colors, images, graphics. We have an idea. You can actually get ideas across to students. I mean, believe it or not. The possibilities of communicating in a much more effective, much more efficient way are enormous. And therefore, carrying out experimentation in that area excites me enormously. Now, I know that you do have a little bit in that country down south from here called the United States, a famous politician who used to be a cyborg in the science fiction world. And I would like, if I may, just to conclude with a few of his profound words, named Arnold Schwarzenegger, for those that don't know. And that is that I have been a cyborg, part human, part machine in the past. And as far as being a cyborg is concerned in the future, I'll be back. Thank you.
Kevin, thank you very much for the presentation. I wonder if I could please ask a first question.
Yes. Well, it depends what it is.
Okay. Well,
Go on.
thank you. You referred to the sensations that you would receive when Irena was moving her hand as a pulse, 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 and several other times in your talk you referred to the neural sensations or the cognitive sensations you got sort of as like pulse, pulse, pulse. But I wonder if you could use those primitive sound wave depressions and other aspects of the human language to really give us what exactly did you really feel? I mean, say more than pulse, pulse, pulse. Tell us what it felt like.
I mean, it is quite a technical thing. I mean, essentially, we opened up a new passage to my brain via the nerve fibers, but my brain had to be retrained to pick up signals via this passage that we'd got. And it really was I mean, for those of you that 80 microamps at 40 to 50 volts. Sorry, this is highly technical in a sense, and rather than an emotive one. At about that current input, my brain was able to distinguish pulses. Now, when we first did it, so essentially I'm there with a blindfold on, my researcher presses a button. Sometimes it injects a current, sometimes it doesn't, but I don't know. And I'm trying to say, yes, it does. So I'm concentrating, trying to focus on that. After about 2 weeks of doing this, my brain was able to get about 70% accuracy, which is not wonderful, but it's a start. And what it felt like was, it was as though there was a charge running up my index finger. So that's the sense my brain was receiving a pulse, and the sense it made of it was, there's a charge running down my finger.
So like for those of us who wouldn't ordinarily have that, is it like when you put your finger in an electric outlet, but not all the way to getting a serious shock, you just feel kind of some electricity?
Feel electric, but it was more of a tickle. I'd liken it when the implant went in, for the first few days, as it settled down, as the nerve fibers settled down, I was getting sort of just ticklings, as you know, like a bit small. You knew they were electricity, but very, very light. This was stronger than that, but it wasn't painful in any way.
Sort of like, okay, and then how about the radar experiment?
Yeah, I mean, then when we did the ultrasonics, because I knew we were doing the ultrasonics, it was the same signals that we were using, but my brain didn't think, oh, that's my finger hurt. It just was able to make that link. There's an object the distance away, because it knew what was happening. And it did that very quickly. It wasn't like I had to have 3 hours moving around before I was able to do it.
Was it that same electric tickle that your brain felt?
Well, it was just it was just picking up a pulse. It was the same actual pulse of electricity, or the frequency was changing, obviously, but it was the same 80 microamps.
How did you subjectively interpret that?
I interpret it that there's an object that is that far away. And it was the same when my wife sent me a signal. That's my wife sending me a signal. So I think first of all, your brain is very plastic. It can adapt and start picking up new signals, but it does make the best guess at what those signals are. Maybe it can get them wrong, but it's able to, oh yeah, that's what we do now, that's what it is. And when it's obvious, I guess we do make mistakes. Our vision often overrides. In the ultrasonic case, I had the blindfold on, so.
Next question, please.
Thank you. Marina Brockway. Dr. Warwick, I commend your dedication to medicine. You stand among the people who did catheterization on themselves to prove the value of that, in my appreciation to you. The question that I have is, as far as I understand, median nerve has also autonomic nerve connection. At least from what I know, is there is an acupuncture point right near median nerve that is implicated in treating ischemia, or at least relieving ischemia. And my question is, did you feel any autonomic response when the nerve was activated?
I have decided, not really. Not that I can report on, no. I mean, I know in terms of acupuncture and things like that, there's obviously an awful lot that we can learn about how we could link the two things together. I think now people are a little bit more open to the links between the two and the potential medical benefits and so on. But in my case, I can't claim that there was any other. I mean, I was looking at it as I've just described in a very technical way, I'm afraid, and just reporting what I could report. So I'd like to say yes, but.
Next question, please. Please introduce yourself and affiliation.
Jun Lee, I'm from Kansas State University, but I work on develop materials to improve the brain, the neuroelectric interfaces. But that work was done while I was at NASA Ames Research Center. And thanks for this exciting presentation. It really, really excited me. Okay, I have two questions. First, with that little robot you controlled with neural cells, and how long do you keep them there? And over that course, while it's learning, did you see any change in terms of the morphology, the number of neurons, and do they develop or they decrease?
Yeah, I mean, the answering those questions through, typically we had put it in for about 1 hour. We've got about 25 brains on the go at any one time, one robot in the pen, and we will put the brain in the robot for about an hour. But what one of the researchers is supposed to be doing now is putting the powered floor that we saw in the original clip, putting that for those little robots, because what we're looking to do is a 24/7 activity. So we can keep the culture. It's actually kept in an incubator with a Bluetooth connection to the robot. So we can keep that in appropriate conditions. And what we're looking to do, this is now futuristic, but is to have it operating in the robot 24/7 so we can witness what's going on in the culture. In terms of changes, yes, we do see strengthenings of pathways in a very big way, but just over the habits, over a week on a week on a week, when we look at snapshots. Now, how was this brain 3 or 4 days ago? It was, oh yeah, look, we can see this pathway now. Of course, we can't ourselves say, yes, this is definitely what this pathway means, but you can hazard a guess. I mean, interestingly, it does happen that Ray was talking to me yesterday about hierarchical nature of the human brain. Well, what we do see in our little culture brains is that sort of thing occurring, that some of the neurons, more by chance, I guess, tend to be sensory neurons, others tend to be motor neurons, and yet others seem to be in a sort of controlling position and rerouting, and as though they're sitting back and saying, hey, you've got to do this, you've got to do that. So the brain within a brain type of thing, and we can witness that just from a habit point of view. But we're clearly learning. Chemically, you can apply chemicals to increase the rate of neuron connection or to decrease it, but to apply signals, electrical signals that in some way are meaningful to the brain is difficult to know what's good other than experience. You say, yes, it seems to learn this better, and if we apply these signals, it does the same thing, so maybe that is a reward or positive function to the brain.
Yep. Second question is regarding that Unither array you implant in your arm. And is any data compare with the implantation people used on the cortex? And also, you mentioned you keep there for 3 months. And do you see any degradation? Clear cell may kind of encapsulated. And,
yeah, it's a good. I have to say, first of all, no. I mean, it was the Utah array, which was later the company Cyberkinetics, and we sort of beat them at it, and I don't know that pleased them all that much. We'd sworn to them that we were only going to do animal studies, and then we went ahead and shoved it in me. They then used it in Matt Nagel, the guy. He subsequently died, but only for monitoring. They didn't actually apply signals. The only feedback there was through visual. They were just monitoring the signals, which was a great shame. But we haven't been able to compare our data with their data. In terms of how the array operated, on the positive side, what we were able to report, when it was removed, fibrous tissue had grown round the array, but it actually acted in a positive way. It pulled it in place, made the connection firmer, and acted as a sort of a bubble wrap, a mechanical protection. And certainly Philip Kennedy, with his from Atlanta, his work, he's described his implants as exactly the same thing. We compared results, and we seem to get the same, what seems to be a natural body response to encapsulate, actually it sort of encapsulates pulling the thing into the neural pathways, so it can work in a positive way. And that's what we witnessed there. So it's far from trying to push it out of the body. It's as though, you know, the nervous system and the brain, it's as though it's a different thing altogether to the body. And so the defensive mechanism is pushing it into the brain rather than pushing it out of the body.
Bob Sklobosky, Computational Diagnostics in Pittsburgh. This is just a lot of fun stuff. I just love it. I have one comment and what was going to be a question, which has probably turned into a comment because of the previous question. But the comment is on the visual experiment you did with the sonar and stimulating the median nerve electrically. And I think that's a very good example of plasticity of the nervous system, namely the nervous system being reorganized. And there was a beautiful series of papers published by Paul Baccarata in the 60s where he took blind people and with pressure stimulators attached to their back was able to recreate their visual experiences. And I think this experiment with a different approach to it does exactly the same thing.
Yes, it fits in nicely.
Yeah, it fits in greatly with that. And my question, and I guess I'm not sure if it's a question or a comment at this point, goes back to the neural mass problem that you have where you grow on the the neurons in the bath and then use those to control the robot. And the way I pictured that in my mind was you had a neural mass and essentially you're performing a conditioning experiment on it. You've got the feedback coming from the robot to one end of the neural mass and somehow you've created an effector output from the other end. And then you go through this conditioning paradigm where the robot hits the wall and you turn something on. And
Yep.
Exactly. So it's a classic feedback kind of thing.
Oh, exactly, yeah.
And what I was picturing in my mind, and I guess this is really my question was, and you've kind of answered it, was the change in the synaptic strengths. And you would predict a Hebbian synaptic property occurring that you should be able to see some synapses, and probably electrically, I would presume you had some electrodes sticking in this mass to also see what was happening at different junctions and things.
We will be. I mean, at the moment, because it's a flat array that it's growing on, so we haven't actually started prodding anything in it. But we have been getting the time sequencing so that we can, whilst the robot is moving around in the corral, what we're trying to get going is a video sequence of the brain, what it's doing in terms of firing activity.
So use fluorescence or something?
Yeah, that's right, in order to show what's happening as the robot gets nearer to the wall. Oh, look, this area of the brain.
Yeah.
I mean, it really is trying to study some of the basics of memory.
Sure.
As to what they are.
Yeah, it's
and where
learning
they
memory, the conditioning. Just a powerful
But I'm
paradigm.
excited. I mean, I ask you, am I allowed to ask questions? I mean,
I'm not allowed to answer.
We have. Okay, well, this is maybe to everybody. We've used rat neurons, which rats are not popular guys, so there's not a problem with that. But we have human neurons now, and we're culturing the neurons. To me, great, you know, because from a medical point of view, this would have much more meaning than in terms of the rat neurons. But the whole thought of what the media does with it, you know, is a robot with a human brain, which is what they're going to say. I mean, how do people feel here? Is everyone, go and do it? Or, well, this is any advice? Or I don't know.
Well, the media will have fun with it, I can tell you that. Actually,
Sure.
There was I don't know if people remember this or not, but there was a fella in Cleveland named Robert White, and he was a neurosurgeon, and his goal was to transplant brains.
Yes. Yeah.
And he did a series of experiments where he would take a living dog and decapitate another dog and attach the second dog's head to the body of the first dog. And so while he was doing these experiments, which kind of actually worked, I mean, in some ways the second head took and didn't quite function right, but was kind of interesting. But the popular press got hold of this stuff, and they had these incredible articles showing, you know, the photograph of a dog with two heads, and, you know, you could see it in the National Enquirer. So you could expect that kind of stuff to come
so
forward.
behead me.
Thanks a lot.
Thank you.
Eric Jacobson, University of Illinois, and perhaps this relates to your question. About a month ago, I went out to the video store for an evening's entertainment for myself and my wife and brought back sleepers, which you're perhaps familiar with. So it seems as though you've done the core work for inventing the orgasmatron. And so it may be that aspect of it, when you go to using human nerves, might perhaps be emphasized.
That'd be more popular. I have to, just as you're going, 3-4 years ago, I spent 3 months as a senior Beckman Fellow at Champaign, University of Illinois, and it was whilst my time there that the work on the rat neurons, that work started, really. That is my time spent there getting me into this work. So thank you for the University of Illinois through yourselves for inspiring that work. And if we do come up with the orgasmatron, then Illinois will be to blame for it completely. Fine. Yes, 10% of all the orgasmatron takings go to Illinois. That's the state of Illinois.
Just as long as it doesn't buy a senator's seat.
Oh yeah, that's much cheaper than that.
My name's Linda McDonald Glenn. I'm an attorney and a bioethicist. I should say recovered attorney and a bioethicist. And I'm intrigued with the ethical questions, and certainly have given much thought to how to deal with this in the press. And there's a lot of questions. Yeah. Do people understand that this is not sentience, or is it? So we get into the issues that we need to talk to the neurologist, the neuro researchers with, because certainly there's an understanding, a concern about pleasure and/or pain that sentient beings experience, which is one of the reasons they shut down that dog experiment. And I was wondering if you had have you heard of the sentience quotient that was developed by Bob Freitas? I mean, there's some issues with it, but some problems with it, but it's at least
I'll look.
Yeah.
I have to say on this point, when we'd just done this research, which is still fairly recent, only to the end of last year for the rat brain, one of the biology assistant professors in my university came up to me while I was just walking across campus and said, "Hey, I've been thinking about this. Do you realize that your rat brain robot, for all the definitions that we have in biology, is alive?" So
right.
So
it's alive, but there's a different. But a cell is a cell is alive too.
Yeah, that's right. Yeah.
I could talk to you for hours about this, obviously. So maybe I can talk to you about this later.
Oh yes. Yeah.
Okay, thank you.
Look forward to it.
Hi, Melanie Swan, MS Futures Group. I'm just wondering what determined the 3-month time frame for the project.
Yes, well, initially I think it was going to be 2 months because it actually, when you're doing that, I was like a walking laboratory. So took up quite a bit, and all we were doing was that. So I really had no time off because you've got this thing in your arm, so you want to use all the time you can to experiment. But we still had things we wanted to do at the end of 2 months. Like the experiment with my wife, we hadn't done by that time, so we continued it for a bit longer. Although the electrodes that were implanted seemed to be perfectly all right, we checked them afterwards. There didn't seem to be any material disappeared or anything like that. Where the wires came out of my arm, they were dying off. They were being broken. Partly because I went in every week, the nurse just checked if there was any infection, and so they were moving around. And I think we ended up, at the end of the 3 months, we had 3 connections left. So all the other wires, and it looked as though it was where the wires came out of my arm. I mean, I don't think that it was designed to have that much moving around, but that was a key factor, that at some point, next week maybe there wouldn't be any connections left, and we had to book up about 2 weeks in advance for the surgery for the neurosurgeon, so we guessed in 2 weeks' time, and we were fortunate we still had some connections but not many left. But it really, I think the overriding factor was I was absolutely exhausted at the end of the 3 months because of doing this experiment in the lab every day, doing that sort of stuff. So that was Yeah, yeah, yeah. Oh, yeah, they were doing all the work and I was having all the fun, but thank you.
Well, it's exactly 12:20. I'd like to thank our keynote speaker for an absolutely fascinating talk. I think, you know, we were talking about whether the device is alive or not. The reassuring thing that people in the field of deciding when, you know, trying to look for life is there isn't any definition. There's a series of characteristics that many of which they have. Oh, yeah. Well, forest fires have some characteristic of life as well. And, but again, this talk has just stimulated our imagination. And it also reminds us of trying to drink from a fire hose. You know, there's so much information that's coming in at one time, but we really appreciate your giving us this very stimulating talk. Thank you. So we're off to lunch, and we're pretty much on time, so we'll come back when as planned. That's great. What's the step?
Yeah, yeah.